Okay, we'll finish section 4.2 with the idea of finding a regression line, but then interpreting the y-intercept. What do those values mean? A slope and y-intercepts, because we found an equation, a regression equation, least squares regression equation. We find it, and it's, remember, this is a linear. This is really a linear equation. And you remember from algebra that is y equals mx plus b. Statisticians prefer, for some reason, they prefer this notation on the bottom right there. But in the end, we'll just use those numbers. And if you had to do it by hand, we would have to do some calculations. Find the standard deviations, multiply by the correlation coefficient, a whole bunch of fancy math. It's fun to do, but we're going to use StatCrunch to find it, which we did up here. We found the regression equation for us right there. That was the regression equation in that example. And so we're not going to do it by hand. We'll use StatCrunch. So here's another example on our note sheets. So we have this data in. You want to put it in. You want to practice finding the least squares regression equation, predicting the drill time. And so this information, sorry, the information. Imagine you're drilling down into the ground trying to get to some oil or something. You're drilling in, and so what happens is the deeper you go, it takes longer to drill 5 feet. So you can see is it gets harder, the rock gets harder underneath the further you go. It takes longer. So what is that relationship? The further you go, it takes longer to drill. Is there a correlation between that? And so I have the data in. So let's go ahead and do that real quick. So I have the data in your, if you joined the group already, this data is there for you. So I have the data. We're going to go ahead and run a regression, not graph, but run a regression equation. Simple linear regression. Depth and time to drill. Is there a correlation? Compute. We look. We take this information right here. And so with this information, then we can make a decision about what that looks like. Here's what the graph looks like with a line. So it definitely looks like the deeper it goes, the longer it takes to drill. So I see that situation there. And then so from here, we want to take this information and then use that information to answer questions like we did before, make some predictions. So let's go ahead and we're going to go ahead and clip that out so we can use it. There it is. Okay, and then so you should be able to get that same information. If you do it, you should practice yourself. Let's go ahead and put that in there. So we have the equation. There's some relationship there, so we can take a look. I see an equation, find the least squares regression equation, and there it is. Time to drill is equal to this. And so again, this is kind of your y, and this is your x. This is your m, and this is your b in terms of slope and y-intercept. So if you look carefully, we have an equation of t is equal to 5.5. I'm gonna round to 2 decimal places. 5.3 plus 0.0. Let's go to 3 decimal places. We always try to keep as many as you can, but for time purposes, we don't need to always keep all of them. 5.527 plus 0.012 depth. And so there's our equation right there. Again, that looks very similar to y equals mx plus b. So in this equation here, we have some important information here for I would say the slope is equal to 0.012, and then the y-intercept, if it means anything, would be 5.527. You got to go back to our algebra y equals mx plus b situation. Okay, part B, predict the drilling time if drilling starts at 130 feet. We have 130 feet here, so we have a value, an observed one. What would our time be if we predicted? And so time would be 5.527 plus 0.012, and then parentheses, and in that place I'm going to put 130. And then what does our equation predict for that? That would be what we're looking at here. And so what we get here when you get that calculation is you get 7.087 seconds. Let me write that, but seconds. That's how long it would take to drill 5 feet. And so we can compare that. This is seconds. Is the observed drill time at 130 feet above or below? Is the observed drilling time at 130 feet above or below or average, right? So in this case, 7.7 is above the observed. So it's above. Our residual in this case is above, or positive, because it's above the observed value. And then I drew the least squares regression line already. And so that was the picture I had. I'm not going to graph it here. That's StatCrunch would do that for us. And so the last thing in this case is we need to interpret what do these mean. What does the slope mean? The slope of the regression line. So that's what you want to think about. What does this number mean? 0.012 and 5.527. What would that mean? And so think about that real quick. And so you thought about the interpretation of slope and y-intercept. I'm going to show you the PowerPoint so you can get that information down to finish here, and that's what you would write in there. As I'm rereading this question, I misinterpreted this question here. It says, what is the observed drilling time above or below? And so if we look carefully, the observed time is 6.93, so it's not above. 7.7 is above the observed time. Let me fix that, please. Observed time is below average, right? This is the predicted based on an equation. This is actually below or faster time than that one. And so to answer your last two questions, here's what you need to look at from the PowerPoint. There's your interpretation of the regression line. Our slope we used was 0.012, and so that was our value. They used one extra decimal point. You can pause it to get that down, to fill that in, and then the last thing is the interpretation of the slope. There you go. That's it. We're done.